let's see what we can do today. New system where I'm trying to draw on these PDFs, so probably going to have some technical issues, but we'll see. Okay, so I think we're doing it. You may have noticed this lecture is rather long-ish. I don't know if we're going to get through it all today, but we will, give it the old college try. So, homework this week. It's week 2, if you're keeping track at home. So on the schedule, there's a line for week 2. Homework, quiz, Friday. No, the Moodle is not up. It will be up before that quiz. Probably right when that quiz starts is when the Moodle will be up. So look for it on Friday. This chapter has been about understanding the transient response of a system. Specifically, we've been focused on systems described by input-output ordinary differential equations, right? Linear differential equations. And we went in depth last time on first-order systems. And essentially, first-order systems are simple enough that we could solve it out sort of in a general case, and we have a table of all of the solutions. And I said that we can use superposition and the differentiation rule, or derivative rule, depending on how the wind catches me, to construct composite solutions or more complex solutions from these simple solutions in the tables. And the same thing is going to be true of second-order systems, although they're a little bit more complicated, so we have a little bit more to do in this lecture. So, big picture, input-output ODEs, we know how to solve them, but we're looking at characterizing the transient response of first and second-order systems, and then remember that higher-order systems actually look a lot like first and second-order systems because they can be thought of as being composed of a bunch of first and second-order solutions. So, yeah, that when we find the response to them, of them two inputs. So, good. So let's go ahead and get started. Second-order systems have input-output differential equations of this form. So this is what we're going to call the standard form for a first and second order, or for a second-order system, I should say. And notice that there's a second-time derivative making it second order. 2 zeta omega n is what we're going to call the coefficient. So the coefficient is just this entire term, right? 2 zeta omega n. Like our typical standard, the coefficient of this term is 1. Coefficient of that term is usually, in the past lectures, we've called it like A1, but we're going to call A1 2 zeta omega n. And we're going to talk about what zeta and omega n are. They're very special parameters for a second-order system. And then omega n squared is the coefficient of y. So we typically call that A0. F of t is, once again, the forcing function. So we call omega n the natural frequency. And we're gonna have a sort of concept of the natural frequency that evolves over time. But you may or may not be familiar with the phenomenon called resonance. And resonance occurs near the natural frequency of a system. If you were to let a system go when it's oscillatory in any way, so a pendulum would be an example. There are a lot of examples like this that are oscillatory. A spring with a mass in the end of it, you let it go, it will oscillate at a certain frequency. That's an understanding of the natural frequency. There's some more subtlety to it than that, but that's a good way to get a good handle on a natural frequency. Those of you who have taken vibrations, I think, somebody in the front row, I don't think anybody else has, but this is a very familiar concept. So, okay. And then zeta is the other parameter that came in. So zeta, it's called the damping ratio. So this is going to be something that we're going to explore in greater depth, but depending on what this damping ratio is, it really affects how oscillatory the system is, okay? So the forcing function in general for an input u is of the form of equation 1.5, where we have coefficients and then time derivatives up to second order of u, although oftentimes these terms b2 and b1 end up being 0, but it's good to keep in mind that in general they can be up to a second order derivative of the input. Systems with two energy storage elements, such as those with an inertial element and a spring-like element, can be modeled as second order, like we discussed. For distinct roots, so lambda 1 and lambda 2, so distinct roots of what? What are we finding roots of? Yeah, characteristic equation, yeah, exactly. So we wrote down the characteristic equation, which is, lambda squared plus 2 zeta omega n lambda. It's panning still, it's hard for me on this system. Plus omega n squared equals 0. And we solved, and we would solve for lambda 1 and lambda 2. That's how we find those roots. So for two distinct roots, so lambda 1 not equal to lambda 2, the homogeneous solution is, for some real constants, kappa 1 and kappa 2, this form. So the y homogeneous, yh, is given here. Remember, if you have a repeated root, you have to add a t in to the second one. Remember that? Oh man, differential equations coming back to haunt you. Oh, I forgot. It's subtle. It's a reference. Don't worry about it. Okay. So lambda 1 and lambda 2, if we solve for them from this equation, we get this expression. Okay? So what happens if zeta if omega n is, well, we're going to go into those details. I actually don't want to get ahead of ourselves. Let's actually go in. We're going to go into great detail on this, or at least some detail. So the free response is the first thing we're going to be concerned about. So this is generally like up through 1.7 is true for all of them, right? The free response, YFR, is found by applying initial conditions to the homogeneous solution, right? That's what happens if you have no forcing, no input to the system. We want to see how it evolves. So it's not going to do anything unless we give it some initial condition, right? There's no forcing, there's no initial condition. If it's 0, it will just stay there. So the initial condition has to be non-zero. And we give it some initial conditions which are common to see. You have to have 2, right? So we're going to give it some offset, y0, and then we're going to give it a derivative of 0. So it's not changing at the initial moment, but it does have some non-zero initial condition. So there can also be the case where you have a non-zero initial velocity, right? Or that was if y is position, but an initial time derivative of your output y. So that should be taken into account, and equation 1.8 does not hold. So it's important to see what went into equation 1.8. So the free response in this case is given by equation 1.8. So there are 5 possibilities for the location of the roots, lambda 1 and lambda 2. all determined by the value of zeta, okay? So if zeta is negative, we call this unstable. So this case is very undesirable because it means our system is unstable and given any non-zero input or output will explode to infinity. So we're going to end up with, if a zeta is negative, that means that assuming omega n is positive, which it turns out always is the case, your lambda 1 and lambda 2 will have a positive real part. Okay? So for those of you who are familiar with mechatronics class, will recognize that as being an unstable system. And it's an important thing to go back and review. It's in the last chapter of the Volume 1 System Dynamics that we went through. But remember that our homogeneous solution is going to be composed of e to the lambda 1 t and lambda 2 t. So if the real part is positive, we're going to have an increasing exponential increase. It's bad news. Exponential increase means it's unstable, means it's going off to infinity, or this sort of terminology, it will explode to infinity. Those are x's. I don't know if you can see those. Those are x's on the eyes. That means bad. I know. We leave no stone unturned in this class. Okay. So, if zeta is equal to 0, that's another case. So there are 5 cases. Here's the second one. Zeta is equal to 0. It means it's an undamped system. An undamped system will oscillate forever if perturbed from 0 input. So if zeta is 0, that means that this real part of the roots goes to 0, right? There's no real part. So it's neither a decaying nor an increasing exponential. Instead, what you have, oh, goodness, typo. Glad you guys came to class. I can just point this out. There should definitely be a J here. Right? In the lambda, oh, you guys can see that, right? Yeah. In 1.7, the equation for the roots, lambda 1 and lambda 2, there should be a J because this is the imaginary part, right? So this term is the imaginary part, this term is the real part. So this is plus or minus J omega n, zeta squared minus 1. So if zeta is 0, that means that, goodness gracious, I tricked myself, didn't I? Did you guys see what happened?
You jumped between 2 different paragraphs.
Yeah, well, that happened too. But I knew there was supposed to be a J there, but I was too quick to put the J there. The J emerges when zeta is equal to 0. It's the square root of minus 1, which is J. That's where the J comes from. So my bad on that. I don't know how to erase. So we take out the J. I mean, you guys take out the J in your own way. I'm going to figure out, oh, look, it worked.
So where do we put it?
It will emerge.
Right there.
Yeah, because zeta is 0, so square root of negative 1 becomes J. However, I have lost my way of trying to figure out how to get my pen back, so meanwhile, we'll work on that. It's like watching your parent try to do computers. It's really hard. It's like maybe the most frustrating thing to do ever. I can't. It's the worst. Yeah.
So the roots are only have imaginary parts when zeta is 0. So like the imaginary part, like you only kind of develop that once zeta is 0.
Yeah. So and then when zeta is positive, but less than 1, this is going to come out to be still negative, square root of a negative number. So it'll still be imaginary.
Okay.
Yeah. Yeah.
And it also works for the negative side, right? If it was less or greater than -1 or less than 0, it'd still be imaginary. Zero squared.
So say that again.
If it's between -1 and 0, it'd also be imaginary.
Yes, that is correct. That's correct. It's that, and that response looks like an oscillating but increasing exponential. Yeah, this is an oscillating. So in a moment, so what we have right now is one that is undamped that just oscillates, right? It just oscillates. Zeta equals 0 gives us a homogeneous solution. So our lambda 1 and our lambda 2 here get plugged into this solution, right? And so for zeta equals 0, we have y homogeneous of t equals kappa 1, and it's going to be e to the, it's j, what's left here is j omega n, right? And then plus kappa 2 e to the minus j omega n. And from Euler's, one of Euler's identities, you can turn this into a sine or cosine. Yeah, so that's pretty fun. So this is the oscillation situation. So just the undamped oscillation. And notice that, so if you turn this into a cosine or sine, omega n actually is the angular frequency of that cosine or sine. So it is exactly the frequency of oscillation when you have zero damping.
Do you get many negative zeta cases like inside of something that someone wants to build? I mean,
No. So it comes into play in a system when you have something that's naturally unstable. So it can happen when you have feedback in a system, when you do feedback control on it. And we'll talk more about that towards the end of this course. It can also happen if you have a system that, like the inverted pendulum problem, where it's unstable,
something
right?
that causes any input causes an output that doesn't get reversed at all. It's like a mouse trap. You step on it and it closes, but it doesn't like snap back open. It just closes.
That feels different to me, but I don't know if I can exactly explicitly explain why. Mousetrap. So
No, that'd be the spring. The spring is releasing a lot of energy, but it's going to decay. It's just that it has
yeah, if you thought about it as a system, a mechanical
It
system,
doesn't oscillate at all.
it doesn't oscillate.
Just like a pendulum, it goes once and decays to nothing. It stays there, but it never goes back.
There's not there's lots of little here. It's like an unstable system.
Well, an inverted pendulum.
So an inverted pendulum is an example. There are other examples. So for instance, there's the ball on top of a hill. If it's balanced up there perfectly, it's fine. But if you perturb it at all, it's going to fall off the hill. That's unstable as well. So you can get into real physical situations that are unstable, and we should be able to see that, but it's not a super common situation. I guess what we're doing mostly in this is we're gonna cut a path through second order systems that's gonna cover a lot of situations, but not everyone. So if you need to, you can always go back if you don't have this case. So we're gonna go more in depth and underdamped and
Yeah, because we didn't talk
whatnot.
about stable systems and vibrations at all.
Yeah.
This is not real.
Yeah, there are certain ways to frame it where you can say that it's not a physically realizable system. However, I don't think that that's a good view. It's not going to come up if you have a simple mechanical system. But when you get very complex, you can get into that. So vibrations has got a lot of really interesting stuff, and I don't want to get distracted because I would love to get distracted, and I'm cognizant of the fact that this material is kind of tough, and I don't want to get caught up in this too much. But the idea is that if you have zeta less than 0, if you calculate it, so if you get a second order system and you calculate zeta and it comes out negative, this section doesn't describe that in detail. It just says, oh, it's unstable, but you still have to go through the analysis of that, which we haven't really talked about. So, and we're not going to get into detail on. But you can always go back to these equation 1.6 and equation 1.7 are totally still valid for that case. So you can go back to here, but you can't start using the material that we're going to develop after this point. So this is the underdamped case now. So that's when zeta is between 0 and 1. Roughly speaking, underdamped systems oscillate, but not forever, okay? So let's consider the form of the solution for initial conditions and no forcing. So the roots of the characteristic equation are negative zeta omega n is the real part. Zeta is positive, between 0 and 1 is positive, right? So this is going to come out to be nice and stable. It's good. What I did here with the roots is I said, okay, well, zeta is going to be positive between 0 and 1. It's going to be less than 1, so I know there's going to be a square root of negative 1 in there. I'm going to just pull it out and stick it right here. And this is where, in my mind, I skipped ahead to. So the j is there explicitly now, and we have 1 minus zeta squared, so we flipped the direction of the subtraction, which is totally fine. And what we did was we define this term, this quantity here, omega n times the square root of 1 minus zeta squared, for the case when you have an underdamped system, so zeta between 0 and 1, to be the damped natural frequency, omega d. Okay? So that is the frequency at which the system will oscillate when it's overdamped and in free response. Underdamped and in free response. However, it is relatively close to omega n. This value of zeta oftentimes so you're taking the square root of it, you're not going to change the value of omega n a whole lot to become omega d. So omega d is the damped natural frequency. It's often conflated. We'll often just say, oh yeah, it'll oscillate at the natural frequency. It's not exactly true. It'll oscillate at the damped natural frequency, but they're often very close. So something to be careful about, but not too bad. So this is the damped natural frequency definition. So the free response formula that we had at the beginning is valid because we have distinct roots. So using Euler's formulas to write in terms of trigonometric functions and initial conditions, y at time equals 0 is y naught, and y dot at time equals 0 is 0, we get this expression here, 1.11. So in this expression, we have our initial condition, we have our zeta, our omega n, contributing to a decaying exponential, right? There's this 1 minus zeta squared square root. That's just a little bit of a factor that's often not too far away from 1. So we have a decaying exponential multiplying a sinusoid, right? And this sinusoid has frequency, the damped natural frequency, and it has a certain phase psi, which is given by equation 112. And this just all comes from converting the exponential form to the trigonometric form. So do you have any issues with that? The Euler formulas are what's being used there, and I encourage you to go back and review how to do that. It's not too bad, but it's just maths. So this is probably a good chunk of our systems are underdamped, okay? second order systems. They have some oscillation, but they're not going to oscillate forever. Your average second order system is going to be kind of like this. Now, okay, so it's an oscillation that decays to the value it oscillates about. So any perturbation of an underdamped system will result in a decaying oscillation about equilibrium. So it's you perturb it from equilibrium, and it's gonna oscillate about equilibrium, but damp back down to it. So perturb it, and it's gonna come back, but do some oscillation. Unlike the first order system, which remember you perturb it, and it just exponentially decays back. So that's a qualitative difference there. So then there's the case where zeta equals 0, or the critically damped case. In this case, the roots of the characteristic equation are equal to each other, and they're both equal to negative omega n. So we must modify equation 1.6, which is our solution to our homogeneous solution, with a factor of t, right? Because you have a repeated root for the homogeneous solution. The free response for initial condition, y naught, and then once again, the time derivative of y being 0 yields equation 114. So this decays without oscillation, but just barely. So if you perturb this system, it's actually not going to oscillate as you let it go, but it's going to be as close to oscillating as you possibly could get without oscillating. Okay? So critically damped. And then we have overdamped, zeta being greater than 1. Okay? So here the roots of the characteristic equation are distinct and real instead of complex. From equation 1.8, with free response to initial conditions y naught and 0, we have the sum of two decaying real exponentials. So if we just go back up to 1.8, it's our lambda 1 and our lambda 2 are just real numbers. So, and they're going to be negative real numbers. So we're just going to have the sum of two decaying exponentials, which tends to look pretty much like a decaying exponential. Sometimes it's hard to distinguish just by looking at it between one decaying exponential and the sum of two decaying exponentials. Sometimes it's really obvious, depending on the relationship between the size of the two lambdas. So, okay, so that's the overdamped case. Figure 1.3 displays the free response results. So let's take a look. And this is so pretty. We just need to recognize that. Good job, me. Okay, so what I'm plotting here is, first of all, these are functions of time, okay? These are the responses that we just derived, the free responses, for the three stable cases, okay? So we have so for the three asymptotically stable, we would call it, so not marginally stable. So the stable cases are, so the first one we did was the underdamped, so the blue, zeta is equal to 0.1. It's greater than 0, it's less than 1, so it's going to be underdamped. So it's going to start out at its initial condition. Notice that I'm plotting here is the normalized output. So I'm dividing whatever it is by the initial condition. So it always starts at 1 because I'm dividing it by whatever it starts at. It's convenient. It's nice. Plotting things like that makes them look pretty is like a strangely important skill, I feel like. So this is underdamped case of zeta equal 0.1. It's going to try to return to equilibrium, but it's going to oscillate about equilibrium before it does. So we get this oscillation, and as we increase the damping, so 0.3 is this curve, so it's going to oscillate less and less. So zeta is 0.5, gets darker, and then the black one is zeta equals 0.1. So that's this this line here that is, it doesn't oscillate. It doesn't oscillate, but it's like super close to oscillating, right? So as close as you can get. It's the boundary one. And then as you increase zeta, so this is the critically damped, so crit. These are all under. And then these are all going to be what? Overdamped. Overdamped. So they're not going to oscillate. And as you increase the damping, they slow down. So if you increase the damping ratio more and more, it's like you're putting the system into, you think of it as like if it's a mechanical system, you're putting it into like a more and more viscous fluid, slowing it down more and more. It's like first you put it in water and it's like slow, but then you start putting it in thicker and thicker oil and it just gets like so slow that it doesn't move very much. It's very lethargic in its response. Okay. So that's our free response understanding for second order systems. Okay, you displace it from its equilibrium, you let it go, and depending on the damping ratio, it's going to respond in different ways. Now, let's talk for a moment about what happens for the other two cases. So we considered the three stable cases, right? So let's talk for a moment what happens if it was, first of all, a marginally stable case, which is when zeta is equal to 0. Okay? So I'm going to draw it with maybe like green. So in that case, and this is going to look awful, I just warn you, it's going to oscillate and maintain. This is totally new, this pen thing to me, so it's just really ugly. But anyways, it's going to oscillate, and its amplitude is going to stay the same. So that is the idea. It's probably easier to just say it, but yeah. But the idea is that this amplitude and this height, they're all the same. They don't change. So that's the case here where it's undamped. And then if we were to go further and we were to make it actually negative, I don't know, I guess I'm using gray pen now. So if we were to say zeta is, say, like equal to negative 0.5, let's say. I don't know how to erase very well. Zeta equals negative 0.5. So in that case, you would get this oscillation happening, but the amplitude would be increasing. Like that, okay? And actually the envelope for this would be an exponential. Look like it's my first time using paint. Okay. Suffice it to say, this has not been the best test run with this system. No. Okay. And then this is, it goes, if we go further, if we go zeta is less than negative 1, we get this unstable, and yet it's in a sense like over damped unstable system where it's just gonna shoot off. This was an envelope, this other one that I drew of this oscillation. This one is not. This is just the response is going to shoot off and not oscillate. Okay?
Systems with stored potential energy. Like systems with stored potential energy. Like a pendulum inverted has energy, and once it's messed with, it releases. It converts its potential energy.
Yeah. Well, so it's like if you had it's like if you had a ball on top of like a sphere or something like that, and you let it go, and it just fell off the side and never came back. That's what it'd be like. I mean, that was probably because if you had a ball that was like maybe magnetic and it was attracted to the top, but like it wasn't enough to pull it back and it oscillated a couple times and then boom, that would be this first unstable one, the zeta equals negative 0.51, where it oscillates but it increases in amplitude until it explodes. Okay, so that gives you the whole idea. We focus a lot on stable systems because oftentimes we don't care that much about what it does when it's unstable. I mean, sometimes we do, but oftentimes we're trying to design a stable system. So we'll just say, if it's unstable, it's not desirable, we're going to change it anyway. So we don't get in depth in analyzing the unstable systems because typically we're just going to change it anyways because we don't want it to be unstable. So that's why we don't get in depth with it. Although it's not, it's irrelevant completely. Okay, the step response is really similar, and so I think we do have time to just go through that and understand it. And then we'll come back on Wednesday and do an example of all this. So second order systems are subjected to a variety of forcing functions, F, of course. In this lecture, we examine a common one, a step forcing. In what follows, we develop forced response, Y, forced solution. So free response is what we just did, so now we're doing forced response. Unit step response are step forcing of the form US, where US is the unit step function, models abrupt changes to the input, right? We talked about that in the first lecture. The solution is found by applying zero initial conditions to the general solution, and that's what we need to develop. So if the roots of the characteristic equation lambda 1 and lambda 2 are distinct, the forced response is given by equation 1.15, which looks a hell of a lot like our other solution, our free response solution, except we've got this 1 minus thing happening here, right? This means that instead of going to 0 with this, so if it's a stable system, instead of going to 0, it's going to go from 0 to some new equilibrium position. So once again, our lambda 1, lambda 2 are given by equation 116 because they come from the characteristic equation, which doesn't depend on forcing, so it's always going to look like that. Once again, there are 5 possibilities for the location of the roots of the characteristic equation, lambda 1 and lambda 2, all determined by the value of zeta. However, there are 3 stable cases: underdamped, critically damped, and overdamped. So the underdamped case, we're going to only consider those in this step response portion. Underdamped, in this case, the roots are distinct and complex. So these are our lambda 1, lambda 2, which are the same as they were in the free response, right? So we just plug in the lambda 1 and lambda 2, and we rearrange just like before using Euler's formulas to get a trigonometric form of it. And we have a decaying exponential term right here, multiplying a sinusoid, and we get 1 minus that. So essentially, we have this oscillation that is happening, but it's decreasing until you get some new equilibrium emerging, which is 1 over omega n squared. This response overshoots, oscillates about, and decays to 1 over omega n squared. So that, it looks a lot, I mean, we haven't looked at the graph, but we will in a minute. It looks a lot like what the free response looked like, except for we're going to a new value instead of coming back to 0. And that's actually identical. It looks identical to that. Critically damped, as the case when zeta equals 1, the roots are equal and real in this case. So the forced step of equation 115 must be modified, right? We have to add the t in, or include a factor of t is a better way to say it. And we get 1.21 as the forced response. So it neither oscillates nor overshoots. It's steady state, but just barely. And then finally, in overdamped case, you have two distinct real roots. And the forced step given by equation 115 is the sum of two decaying real exponentials. So I didn't rewrite it because it's just 115 with real lambdas in there. So it's nothing really to write down. And then we can look at the figure. Okay. So let's take a look at that. The system for a forced response, we have initial conditions set to 0, which sometimes we will abbreviate by just saying 0 initial conditions. So we always start out at 0. And we're going to go to our new equilibrium value, which is 1. So I multiplied every response here by omega n squared. And since our new equilibrium is always 1 over omega n squared, they always end up at 1 in this graph, because it's nice that way. And our different zeta values are given here. So zeta equals 0.1 is an underdamped case, right? So underdamped is going to oscillate and decay to the final value. And then as we increase the damping, it's going to oscillate less and less. Finally, we get to the critically damped case, where it doesn't oscillate, but just barely. And then we get to the overdamped case where it oozes. So a step response, actually, we learned, a sort of new aspect about these today too. So a step response actually looks a lot like a free response. But instead of starting at some initial condition, non-zero initial condition, and decaying to 0, you start at 0 and go to some non-zero equilibrium value, new equilibrium value. So this looks just like the other one, just inverted. Now, on Wednesday, we're going to move on to some new material, a new sort of chapter, but we're also going to finish up this work by going through an example with superposition. So, see you guys on Wednesday.